In this video, we will talk about optimal combining. So currently we are discussing the different forms of combining, that is how we can combine the signals at the receiver. So let's say we have a receiver and we have m number of antennas at the receiver. And the combined signal yt is equal to the sum of the signals received at all the antenna element, provided every branch has given some particular weight alpha I. So then we can write the received signal y is equal to alpha 1 y1 plus alpha 2 y2 plus so on alpha m ym, which can be written in this form: summation over all antennas. We have weight alpha I corresponding to each of the branch, and then we have hix plus wi. Hi is the complex coefficient corresponding to the ith branch, and then we have wi, the noise corresponding to the ith branch. And for the ith branch, we can also compute the SNR, which is given in this form, where we have noise variance corresponding to the ith branch. So now the problem statement in optimal combining is as follows. We have to find an optimal set of alpha I. That means the weights. What are the weights that to be provided to each of the branch such that the resultant SNR of this Y is maximized. So then we can expand this equation. We have yt is equal to summation over all number of antennas. We have alpha I hix plus summation over all antenna elements. We have alpha I times wi. So we have this signal term and we have this noise term. So we can easily compute SNR. SNR is norm square summation I is equal to 1 to m alpha I hi corresponding to the signal term, and then at the denominator we have the term corresponding to the noise with sigma n square I, that is the noise variance corresponding to the ith branch. So then next we will do some manipulations using this Cauchy-Schwarz inequality, which states that the absolute values of the dot product of two vectors is less than or equal to their individual product. And this is inequality when this a and b, these two vectors, are dependent. Otherwise it is less than or equal to this. So we will exploit this Cauchy-Schwarz inequality in this SNR form. So now let us focus on the numerator part. So we can write numerator part as this. We multiply divided by sigma n comma I by sigma n comma I, such that they both get cancelled out and we get this again the same form. So consider this term as A and this term as B. So using this inequality, we can write it in form less than or equal to this A, and here we have B. So now again, if you look at this expression here, what you can see is that this term is equal to the denominator of the SNR. So whenever you substitute this expression into the SNR in the numerator, this term and this term, they will get cancelled out with each other, and what you will get is the SNR is equal to summation over all the branches times mod hi square upon sigma square n comma I. So you will get this particular form. And what is this? This is nothing but gamma I, the SNR corresponding to the ith branch, which is also defined in this particular expression. Gamma I is equal to mod hi square upon sigma square n comma I times es. So then we have summation over all the branches multiplied by the SNR of the ith branch. So from here, what we can say that is the best SNR that we can obtain is the sum of the SNR corresponding to each of the branch. So that means the best that we can obtain is the sum of all the SNRs of each of the branch. That means gamma 1 plus gamma 2 plus gamma 3 plus gamma 4 and so on up to gamma m. This is equal to gamma MRC, and this is the best possible that we can achieve. And this depends upon what is the value of alpha I, or what is the weight that we chose on each of the branch. And it has been proved that if you choose this alpha I to be equal to HI conjugate by sigma square n comma I, then you will have this gamma opt will be exactly equal to the sum of SNR of each of the branches. And this alpha I is nothing but this. In the numerator we have coeffacing, and in the denominator we have this noise variances corresponding to each of the antenna element. So we are doing coeffacing, but we are also adding the complex gain to the coeffacing based on the noise variances of each of the antenna elements. And when in this case, when the gammas of all the branch, they are exactly same or approximately same, then in that case gamma opt will be equal to m times the SNR of one of the branch, and we will have a linear increase in the SNR, and this is the best form of combining that we know till date, that is the maximum ratio combining. So combining, we are combining the received signals, different received signal. We have Y1, we have Y2, we are combining all these signal, and then we have ratio because we are providing different weights, or we can say we are doing weighted coeffacing. And corresponding to the noise variances, we are applying the different weights to it. So what is the intuition behind this maximal ratio combining? So for intuition behind this, we first have to go to the case of coeffacing. Let us say we have two different branches. We have antenna branch 1 and we have branch 2. We have SNR 1 and we have SNR 2. Now let us say that the SNR of the second branch is very less than the SNR of the first branch. Then in case of coeffacing, the noise in SNR2, noise variance of SNR2 is very high, and this will impact the SNR of the best branch. But whereas in case of maximal ratio combining, what you are doing, since maximal ratio combining alpha I is equal to HI conjugate upon sigma n square comma I. So let's say for the second branch, this is alpha 2 is equal to H2, and this is sigma n square 2. And for the first branch, we have weight. This alpha 1 is equal to HI conjugate upon sigma n square comma 1. So since this noise variance is very high, so you will select alpha 2 to be very small. And whereas in this case, the noise variance is very low in case of first branch, you will select the weight corresponding to this branch to be very high. So in this case, the noise of this second branch will not impact the SNR of the strongest branch. So this is the intuition. So that's why we have this. This is because of the result that we have alpha I is equal to HI conjugate divided by sigma n comma I square. So thus, when this value, the denominator part sigma square ni noise variance increases, you give lower weight by dividing it, and then alpha I will only depend on the noise variance. Okay, so what is the additional thing that we need to do in case of MRC compared to the coeffacing? So what we were doing in coeffacing, what we are doing is we are first estimating the complex rotations provided by the channel, and then at the receiver side we are compensating that rotation. But here we are doing that It's okay. We are doing the same thing here, but additionally, we are also estimating the noise variances corresponding to each of the branch. So this system is more complex. If you do not have any complexity constraint, then you can stick to MRC. Otherwise, you can select cophasing based on the complexity required. Okay, so we have some observations about MRC. So the first observation is that alpha I is directly proportional to HI conjugate. So the best channel will have a higher fade. So when the antenna is noisy, you do not give much gain to it. When the noise variance is high corresponding to the branch, then the weight will decrease. So, and we need to estimate both the HIs and we need to estimate the noise variances corresponding to each of the antenna element. And when all the antennas, they have equal strength, in that case, gamma MRC is M times gamma bar, that is the SNR of any of the branch, and it grows linearly as we increase the number of antennas. And even if the gamma I is less than gamma TH, by combining in this form, gamma MRC may become greater than gamma thresholds. So that means even if some of the branch they are in fade, the gamma MRC will always be greater than gamma TH. Not always, but there could be a situation where this gamma MRC is greater than gamma TH, even if all the branches or the SNR corresponding to the ith branches is less than gamma threshold. So whenever you use different form of combining, let's say MRC or SC or cophasing, we are basically changing the statistics of the SNR. So we want to compute the PDF of SNR. So we will not go into much detail. We will assume that this is the PDF of the SNR, and then we will see what impact it will have on the probability of error. So when we compute the probability of error in case of dBPSK, what we get this expression. This is half multiplied by 1 plus gamma bar raised to the power m. And for high SNR, when this gamma bar is greater than 1, we can write it in this form, in the approximated form, 1 divided by 2 gamma bar m. And this is basically changing the slope of the probability of error. So this means for a BER plot versus SNR in dB. So if this is for m is equal to 1, so moment we add another antenna, the slope is changed. Slope has been shifted to the left. So this is for m is equal to 2 and this is m is equal to 3. So as we are increasing the m, it changes the slope of the BER plot, and this m here is called as the diversity order.